that everybody's on the same page about what does pKa actually mean. So lower pKa, more acidic, easier to lose a proton. And then once you deprotonate that acid, you get the conjugate base. So we're gonna be talking about all those things today. Okay, so we're just gonna introduce carboxylic acids. So describe their structure and bonding, and then their physical properties. So understanding melting point, boiling point things, and then predicting pKa trends. All right, so let's get started with our first learning objective. So this is chapter 19. We're going to describe the structure and bonding of carboxylic acids, which is section 19.2. So we're just going to start with the most basic carboxylic acid. So the simplest one that looks like this. Let's draw in our lone pairs. So, okay, so if this substituent right here is a hydrogen, this is called formic acid. But what we're about to talk about is general about carboxylic acids. And if we look at this, most people can probably see that this carbon and this oxygen are both sp2 hybridized. But this oxygen is kind of special. It has two bonds, right? This OH bond, this O carbon bond, and two lone pairs. So kind of following our conventional rules, that would be sp3 hybridized. But in this case, it's actually not. It is also sp2 hybridized. So that's weird. So why is that? Because of resonance. So we can draw a couple of resonance structures for carboxylic acids where I can push one of these lone pairs to make an O carbon double bond. And then I push that pi bond up into the other oxygen. Remember our resonance arrows, we have heads on both sides. So now I have a double bond going in this direction. That oxygen has one lone pair and a positive charge. This other oxygen now has three lone pairs and a negative charge. So we sort of pushed the electron density from one oxygen towards the other. Now there's another resonance structure, which is not as stable, but it does exist and it is useful. So I'm going to draw it also, which is when the central carbon is deficient. So instead of having the oxygen be the positively charged thing, I can also have this central carbon be the positively charged thing. Like so. So those are our three resonance structures. Again, hopefully you feel comfortable drawing different resonance structures. And so looking at these resonance structures, we should now be able to understand why this oxygen is sp2. In this center resonance structure, that oxygen looks a lot more like sp2, right? So now we have that double bond to oxygen, or to carbon, excuse me. The other couple of things that we can notice is that this resonance structure, where we have positive charge on carbon, where it's deficient, right? It actually has like an empty orbital. This is showing that that carbon is electrophilic. So that becomes important later. We just wanted to point that out. And then the other thing is that what in the neutral structure on the left is the carbonyl oxygen. In the other two resonance structures, that's the negatively charged one, right? So right here and right here, we have that negative charge. So that means that that oxygen is the most electron-rich site. Here and here. So that might not be obvious from this neutral structure. Totally get it, right? It's kind of hard to see. But this is why resonance is really important. So you got to remember that the actual structure is an average of all of these resonance structures. So in two of those resonance structures, that oxygen is negatively charged. Therefore, it has the most electron density. Okay? So why does that matter? That matters because if we were to protonate, so we add an acid to a carboxylic acid, that's where it's going to protonate. So Let's redraw our carboxylic acid down here. Like so. Okay. So if we now add a strong acid, so let's say H2SO4. Like this, it's going to protonate the carbonyl oxygen because that's with the most electron density. So we're going to push from our oxygen lone pair, and then this pi bond is going to break, and then that carbonyl is going to grab the proton. Okay. Let's draw what we get from that. And then HSO4 minus is our counter ion. And now we can actually draw two resonance structures of this where we have that positive charge on either of our oxygens. Okay, so once we protonate a carboxylic acid, those two oxygens are now completely indistinguishable, right? They look the same because these two resonance structures are functionally identical. Yeah? All right, so that's what we want you to know about the structure, right? This oxygen, carbon, oxygen, all of those are sp2. And because they're all sp2, that means that they're all in the same plane, right? So it's flat. Okay, so oxygen, carbon, oxygen, all of that is flat in one plane. We want you to know the carbon here is electrophilic. We want you to know that the carbonyl up here is the most electron-rich site, such that that's where it would be protonated if you were to protonate it. Okay? Okay, so now let's talk about our next learning objective, which is about the physical properties. Of carboxylic acids, which is 19.3. So again, this is where we're usually talking about boiling points. And anytime you see boiling points, the first thing that comes into your mind should be intermolecular forces, okay? Hydrogen bonding, dipole-dipole interactions, those types of things, okay? So we're gonna compare a ketone to an alcohol to a carboxylic acid. Okay. So we're purposefully trying to make each of the molecular weights about the same, just to compare. We're going to compare the boiling points in degrees C. So our ketone here has a boiling point of 80, and our alcohol has a boiling point of 99. So we've previously talked about that, right? Alcohols have that OH group. So now we have hydrogen bonding, so it has a higher boiling point than ketones. So when we go to carboxylic acids, right, we also have this OH group. We also have this carbonyl. So our boiling point actually goes up to 141. So that's a pretty big jump, right? This is much higher. Okay. So if it's a much higher boiling point, that means that it's going to have very strong intermolecular forces, or IMFs, right? Strong intermolecular forces. Probably hydrogen bonding, because it's usually hydrogen bonding. Hydrogen bonding is the strongest of those intermolecular forces. Okay. So why is this? Hydrogen bonding. Okay, so we now need to draw something that's a little bit challenging to draw, which is a carboxylic acid dimer. So I'm going to draw one in blue in this orientation. And I'm going to try to draw one upside down. We're going to do that in green. HO, like so. Okay, so it's just two carboxylic acids where one's kind of flipped upside down. And we could make sort of these hydrogen bonds in between the OH of one carboxylic acid and the carbonyl of the other one, right? And we can do that twice. So that is a like really, really strong two hydrogen bond interaction, okay? So really strong hydrogen bonding, so strong intermolecular forces. Or the other way you can think about it is that we're sort of making this dimer, right? So we're bringing two of them together. And so that means that we're effectively doubling our molecular weight, which is going to cause our melting point to go up and our boiling point to go up, right? Because higher molecular weight things have larger boiling points. Okay, so two different reasons, but probably the easiest one to remember is strong hydrogen bonding. That's usually the answer when we're talking about boiling points. Questions on any of that? Kind of our structure and bonding, just introduction to carboxylic acids. Yeah. Yeah, dimer is when you have two of the same thing coming together. We have two carboxylic acids that are sort of making one molecule-ish, right? It's not actually one molecule, but they're like strongly associated with each other. Yeah, good question. All right, so that's kind of our intro to carboxylic acids. So now for the rest of the class and on Monday, we're gonna talk about pKa, right? It's a carboxylic acid. So I bet it's an acid. So that's what we're gonna be talking about. So this is learning objective 19C. We would like you to predict our pKa trends of carboxylic acids. So we're going to kind of go through 19, 4, 5, and 7. Okay, so just starting with kind of basic acid-base chemistry, right? So carboxylic acid. The reason that acid is in the name is because it is the most acidic compound with only carbon, hydrogen, and oxygen atoms, right? We can get much stronger acids when we introduce sulfur or heteroatoms, right? But with just carbon, hydrogen, oxygen, carboxylic acids are the most acidic. Okay, so that means that they're pretty easy to deprotonate. So let's look at an example. So now we'll look at acetic acid. So now if we have a methyl group here, right? So instead of a hydrogen, we have a methyl, that's called acetic acid. This has a pKa of 4.7. So we mix this with water. We're going to deprotonate. And form H3O+. We're going to compare this to an alcohol. So if we mix an alcohol with water, we can form an alkoxide plus H3O+. But the pKa of an alcohol is about 16. All right. So that's very similar to water. So I drew our equilibrium arrows on the right side for the alcohol, pretty balanced, right? It's pretty balanced because all those pKa's are pretty close. Whereas when we have a pKa of 4.7, it's really going to push that equilibrium to the right because it's really easy to get rid of that proton. Okay? So why do we have these very low pKa? So there are two reasons. The first is our good friend resonance. Okay, so once we get to this deprotonated conjugate base, I can draw a resonance structure where I spread that negative charge between our two oxygens. like so. This is called a carboxylate. It's just the name of the conjugate base of a carboxylic acid. Right? 8 generally means negatively charged. So carboxylate, negatively charged version of a carboxylic acid. Okay. And again, let's recognize that these two resonance structures are functionally equivalent, right? They're the same. So that means that our two oxygens, again, are indistinguishable. So you'll actually sometimes see it drawn like this, where we kind of have like a half double bond on each of them. And then that negative charge is sort of shared between the two. So this red bond, right, is the one kind of going up here. And this blue bond is sort of the one going down here, right? So they're functionally equivalent. And so that means that these CO bonds are equal, so they're the same length. And that negative charge is on both oxygens. So this is just kind of another way of drawing it, where it's sort of like a halfway between the two resonance structures, right? So sometimes you'll see that kind of drawn in this halfway structure. Okay, the other reason besides resonance that we have a low pKa is induction. So remember, induction means that we're pulling electron density towards something through bonds. So in this case, we have that carbonyl oxygen is an electronegative atom. So we think, like, maybe I'll show it on this first acetic acid here, right? This proton is quite acidic because electron density is getting pulled towards the carbonyl, right? So it's pulling electron density away, which makes it more acidic. Okay, so both resonance and induction are why carboxylic acids have such low pKa's. All right, I'm gonna take a little bit of an aside to talk about that carboxylate. So this conjugate base for a second, which is 19.7. So we said that when you have a carboxylic acid, you can mix it with some strong base. So like sodium hydroxide, for example. That base will pull off the proton and make your carboxylate. Okay, so again, this is technically equilibrium because it's acid-base chemistry, but our KEQ is so large, it's like 10 to the 11. So it's just like, it's essentially irreversible, that we are essentially 100% making this carboxylate salt and water. So in this case, I showed sodium hydroxide. So we would be making sodium carboxylate. But it doesn't have to be sodium, right? I could have used potassium hydroxide and then it would have been potassium carboxylate, right? But it doesn't have to be hydroxide. Any strong base will do this. And so as a reminder, we've learned about a lot of strong bases. So any organometallic is a strong base, so it can do this. Any negatively charged oxygen, alkoxide, for example, right? So alkoxides, amines, so NR3, so neutral amines, neutral nitrogen, or negatively charged nitrogen, like amides. Those are even stronger bases. So any of those, any strong base is going to fully deprotonate your carboxylic acid. So that actually limits the types of chemistry that you can do, because oftentimes it just deprotonates and then it's done. It just sits there. Okay. So that will come back as a theme of like, oh, well, we wanted to do this reaction and then actually you can't with a carboxylic acid because it just deprotonates. The other cool thing about these sodium carboxylates is that they are often water soluble. So the sodium salt and like the potassium salt, for example, right? So if I were to use KOH instead, are often water soluble. So that means practically when you're doing chemistry with a carboxylic acid, if you want to get rid of the carboxylic acid, or if you want to separate it from other organic things, you can extract it into basic water, and then the carboxylic acid will get separated. So we can extract our carboxylic acid into aqueous sodium hydroxide or aqueous potassium hydroxide for separations. So that's just like a practical consideration. If you're taking 2311 right now, maybe you've done that or talked about that. So extractions, right, are really powerful for separating water-soluble things from not water-soluble things. Most of the time, organics are not soluble in water. So this is kind of a special exception that you can make carboxylic acid soluble in water just by deprotonating them. All right. Questions on that? Cool. Yeah. Okay. All right. So now let's talk about what happens. What's this R group, right? So kind of just been generically talking about pKa's, but we want to talk about pKa trends. So we're comparing different carboxylic acids to each other. How do we know what has the lowest or highest pKa? So this is section 19.5. So now it's going to be substituents and acid strength. So how does that R group on our carboxylic acid affect our pKa? So again, this is our kind of generic equilibrium that we're talking about. Like so. All right, so now we're talking about this R group here. So if R equals alkyl, so we talked about acetic acid already, right? So that's a methyl group. But if we were to have like a much longer alkyl chain like this, or like a tert-butyl group like this, okay, we can compare those pKa's. So we said acetic acid was 4.7. So that's going to be kind of our benchmark that we're comparing against. The other two, 4.9 and 5.1. Not that different, right? Those are pretty similar. Those are all really close to 5. So this is not a big effect if it's just an alkyl group, right? Just carbons and hydrogen, sp3 hybridized, right? Like not a big effect. Just alkyl groups, not a big effect. It starts to become a bigger effect if you start introducing halogens or very electronegative atoms. Okay, so if R, so first talk about alpha halogens, so in the alpha position. So remember that halogens are an electron withdrawing group, right? They're very electronegative. So we can look at this series. So again, let's remind ourselves that the carbon next to the carbonyl, not the carbonyl carbon, but the one next to it is the alpha carbon. So if we keep adding a chlorine to that alpha carbon, so there's 1, I can also put 2, or I can put 3. Okay, so all I'm doing is replacing a hydrogen with a chlorine as I go from the left side to the right side. Okay, so that chlorine is pulling electron density towards itself, right? It's inductively pulling that electron density. So again, those little carets means that it's pulling electron density towards itself. So if we could compare our pKa's, again, 4.7 for acetic acid is sort of our benchmark. Adding 1 chlorine drops it to 2.9. Again, we pull electron density away from the acidic proton, makes it easier to take the proton. If we have 2 chlorines, it goes down to 1.3. And if we have 3 chlorines, it goes down to 0.9. So that shows that adding these alpha halogens lowers our pKa, right? So for every one that we add, we're getting lower. So this is an additive effect. So 1 halogen lowers it, multiple halogens lowers it more. Right? So it's an additive effect. And it's because of induction. We're pulling electron density away through the bonds, making that proton easier to take. Yeah? Yes. Making sense?
With all due respect, sorry, I paid $50,000 a semester to listen to her talk. I don't.
Hey guys, in the back, can you stop chatting, please? Other people would like to pay attention. Yeah? Thank you. Yeah. Questions on this? All right, let's do a timing question to see if that's making sense. And if we can apply our knowledge of different groups here. So again, which carboxylic acid has the lowest pKa? So we have 4 different carboxylic acids with different groups in the alpha position. A fluorine, a chlorine, a methyl, and a hydrogen. Okay, feel free to chat with your neighbors about it. Whenever you see a question like this, make sure you check, is it asking for the lowest pKa or the highest pKa? Because sometimes we'll ask for either. Sometimes we'll ask for ranked, but in this case, we're asking for the lowest pKa. Okay, maybe 15 more seconds to get your answers in. See what we got. Excellent, great job. Okay, so most people are getting that the A that has the alpha fluorine is going to have the lowest pKa. And then after that, the chlorine, which were both really, really good answers. So excellent job. Let's draw this out and look at why that is. So our 4 options here. we're alpha fluorine, alpha chlorine, alpha methyl, and then a hydrogen. Just had two hydrogens there, right? So most people were getting that this one is going to have our lowest pKa, and that's because of this fluorine right here, right? Let's remind ourselves that fluorine is the most electronegative atom. So when we're talking about inductive effects, right, it pulls more electron density towards itself than any other atom. Therefore, it's going to lower it the most. After that, it would then be the chlorine, because that's the other halogen, right? These two are pretty similar, right? Again, alkyls don't really affect pKa that much. And so these last two are going to have higher, about the same. Yes. Uh-huh. Yes, that's a great question. So yes, if you're using a strong base, so just another example of a strong base would be like a thiolate, S minus. Yep, absolutely. Yep, good question. Okay, so that's alpha halogens. Okay. Yes.
What is the impact of adding an R group that has an alkene or an alkyne in it?
Yeah, we're about to get there. It's coming, I promise. Okay, so halogens, I think, are the easiest to start with, right? Because we're pretty comfortable with halogens being electron withdrawing, but they're not the only electron withdrawing group. So we are going to talk about other electron withdrawing groups. Okay. So, for example, if we have a methoxy in the alpha position, this is also an electron withdrawing group. So that might sound strange to you, right? Because we've been talking a lot about methoxys as electron donating groups in like electrophilic aromatic substitution, for example. But this is different because we do not have the same types of resonantly donating, right? This is all induction. And so this oxygen is an electronegative atom that's pulling electron density towards itself. The other way to think about it is this molecule has a dipole that's going in that direction, right? We're pulling electron density away. We have that dipole in that direction. And the pKa of this guy is 3.6. So remember, we're benchmarking against 4.7. So this is lower than acetic acid. So we have this dipole away. Again, inductively withdrawing. So our pKa goes down. Okay. So again, we cannot do this. No resonantly donating. There's nowhere for it to go, right? We would have to break a sigma bond in order to make that happen. So we don't have resonance here. It's just induction. So that's why it goes down. Okay. So if we then increase the size of that dipole, it has an even larger effect. So, for example, if we put a CN group, right, a cyano group, now we have multiple bonds to that electronegative atom. Oops. Right? So that means that that dipole is going to be even larger in that direction. So that will lower our pKa even more to 2.5. We've got this larger dipole equals more electron withdrawing, means that our pKa goes down even more. So this is related now to the alkenes and alkynes. We do not have an electronegative atom, but it will lower it relative to an alkyl, but not as much as if you had a heteroatom. Yeah. Okay. if we go even more electron withdrawing, so if we were to add a nitro group, for example, so let's remind ourselves what a nitro group looks like this. So this nitrogen is actually positively charged, right? It's actually positively charged. And it has, so we're kind of pulling electron density towards this oxygen, we're pulling electron density towards this oxygen, and that atom is actually positively charged. That means we have a really large dipole in that direction. So that positive charge goes to a very large dipole. So that means that our pKa should go way down, and it does. Our pKa for this one is 1.7. Okay, so this is kind of how we can understand how electron withdrawing something is. How large is that dipole pulling away from that acidic proton? Okay. All right. So that's sort of like the first rule, I guess, when thinking about substituent effects, right? What is the electronegativity, or what is the dipole away from the OH? So these are our inductive effects. So that first one is about electronegativity, or the strength of the dipole. Right, so that's kind of the first factor you need to consider when trying to think about the trends. The second factor that you need to consider is the distance from that carboxylic acid. Okay, so we've so far been talking about adding that electronegative group to the alpha carbon. But what if it's not the alpha carbon? What if it's farther away? So let's look at that. Okay, so here is what we've been talking about. So that's the alpha carbon. So I can put my, say, chlorine there. Or I can have the alpha beta carbon. We can put our chlorine on the beta carbon. Or we have alpha, beta, gamma. We can put it on the gamma carbon. Okay. So we compare the pKa's of these three. The alpha carbon has a pKa of 2.8. Beta carbon, 4.1. Gamma carbon, 4.5. Okay, so what does that mean? Our lowest pKa, right, is the one on the left, has the heteroatom closest to the carboxylic acid, right? And then as it gets farther away, it has less and less of an effect. Okay, so the closer it is, the bigger the effect. Two and three. Okay, so those are kind of the two major considerations that we want you to be thinking about when thinking about pKa trends. So today we've been talking about alkyl, right, carboxylic acid. So we do not have any of that resonance effects. On Monday, Juan is going to talk about some aromatic carboxylic acids where you might start to think about that a little bit more. But in general, the key message, anytime you're trying to compare pKa's, is you're going to ask yourself, what will stabilize that carboxylate, right? So the conjugate base, so that carboxylate negative charge, the best. Right, so we think about that. We deprotonate, we form a negative charge. The more that negative charge has to just sit on one atom, the least stable it is. But the more we pull electron density away from that negative charge, the more stable it is, right? So that's why having more electron withdrawing groups is helpful, because you're stabilizing the negative charge. That makes sense? It's kind of like different ways of thinking about it. And I think that different people's brains work differently. So trying to just show it to you in a couple of different ways. But in general, anytime you're thinking about pKa trends, what stabilizes the carboxyl or the carboxylate, the negative charge, the conjugate base? That's generally going to be true. But there are different ways that you can stabilize it. Today, we've been talking about induction, because alkyl carboxylic acids really only have induction, right, from those substituents. Okay, let's try one more chiming question to see if this is all making sense. Okay, so here is another way of phrasing essentially the exact same question that I asked you before, right? Which of the following carboxylates is most stable? Okay, so don't get confused if the question is phrased differently. We're still testing the same learning objective, but you should recognize that the stability of the carboxylate is related to the pKa of the carboxylic acid, right? So those are two different ways of asking the same question. So again, we're just looking at different substituents on this carboxylic acid, or in this case, it's all CF3 groups or CH3 groups, and then looking at distance. So once again, welcome to chat with your neighbor, see if that's making sense. See if you agree. Give 10 more seconds, get your answers in. All right, see what we got. Yes, good job. Okay, C is the correct answer, right? It has CF3, so we have 3 very, very electronegative atoms, the closest to the carboxylic acid. That's great. So it kind of combines these two inductive effects that we've been talking about. Let me draw that out real quick. So we had a CF3, I don't know why I drew that so high. CF3 carboxylate. We have it one closer. We have it directly attached. Or we have a CH3. Okay, so first we have to recognize the stability of the carboxylate, right? Meant that the carboxylic acid was the most acidic, so which one's going to deprotonate the most. And so the one that has a CF3 group directly attached, right? Directly attached to that carboxylic acid is going to have is going to be the most stable. So this would be the most stable. If we were to rank these, the next one would be where the CF3 is 1 carbon over, right? So a little bit farther away. At this point, it's probably this one, but it's pretty far away, so it might not make that big of a difference. So again, 3 and 4 are going to be pretty similar to each other because it's so far away. It doesn't matter as much, but CF3 is a very strongly withdrawing group. And so it probably still has a little bit of an effect, even though it's pretty far away. Questions on any of the things that we talked about today? Okay, so we might ask you pKa higher or lower. We might ask you carboxylate, more stable, less stable. It might have to do with the strength of the dipole, the number of groups, the distance from the carboxylic acid, right? All of these trends are the same anytime you're talking about pKa's, okay? Great, that's all I have for you today. Thank you very much and good luck.